Linear approximation, sometimes called linearization, is a process that we can use to find a really good estimate about the value of a function at a certain point that we don't know by using some information that we have about the value of a function at a point that we already know. Basically, we're using the fact that at a given point on a function, let's call it x1, y1, the tangent line at that point runs really close to parallel to the graph of the function for x values that are close to x1. This is really useful in cases where the function we're dealing with is especially complicated, and finding the y value of a given x value proves to be a difficult process. For example, it can take this equation and turn it into this equation. The second equation may look harder, but without a calculator, the second equation is definitely easier to solve than the first one. Although the answer to the second equation won't be exactly equal to the answer to the first, the approximation made by the second equation could be good enough in a lot of circumstances. If the y output of the second equation is easier to find than the first, and the two answers are close enough, why wouldn't we just use the second equation? For example, linear approximation can be really helpful when we're trying to estimate square roots, since we already know lots of other square roots like the square root of 4, 9, 16, and so on, but we don't really know how to take the square roots of numbers that aren't perfectly square, like 3 or 9.2. Let's go ahead and look at how we can use linear approximation on the square root function. Let's say we want to find the square root of 16.3. That sounds pretty tricky, but we already know that the square root of 16 is 4. So we could say with at least some confidence that the square root of 16.3 is going to be just a little bit more than 4. Let's try using linear approximation to get an even better idea of what this square root might be. We'll use the information that we do know, that the square root of 16 is 4, in order to estimate what we don't know. If we take a look at the graph of the function f of x equals the square root of x, we can mark the point here with coordinates 16, 4. We know the square root of 16.3 is going to be nearby, so what we can do is draw a tangent line to the graph at the point we do know, and then use the equation of that line in order to find a y value for x equals 16.3. Finding the equation of that line is just a matter of recalling the point-slope formula and plugging in the information we have. The point-slope formula, remember, gives us y minus y1 is equal to the slope multiplied by x minus x1. Using the point 16, 4, we have that y minus 4 is equal to the slope of the line multiplied by x minus 16. The one thing we're missing in this equation is the slope of the line. But we're using the tangent line to the function at the point 16, 4. And how do you find the slope of the tangent line at a point? You evaluate the derivative of the function at that point. So the slope of this line is going to be equal to f prime of x1, or in this case, f prime of 16. The derivative of the square root function is equal to 1/2 x to the power of negative 1/2. So at x equals 16, the slope of the tangent line is 1/8. The equation for the line we're using for our linear approximation then is y minus 4 equals 1/8 times x minus 16. After a bit of algebra, we get the simple equation y equals 1/8 x plus 2. Now all we need to do is plug in 16.3 for x, and that's going to give us 16.3 over 8 plus 2, or just 4.0375. This method isn't going to give you the exact value of y on the original function, but since the square root of 16 is so close, the linear approximation will give you a pretty good estimate about the square root of 16.3. Looking at the graph of the function, plus the tangent line that runs through the point 16, 4, we can see that we get really similar values when we plug 16.3 into the original function and into the tangent line. In fact, the actual square root of 16.3 is 4.0373, so the answer we found seems like a pretty good estimate. So if you think about linear approximation, you can say that, in general, you can find the linear approximation at a point x2 when x2 is close to x1 and when you already know information about x1. You just plug the information you have into this linear approximation formula, which is really just a generalized version of what we used in the previous example. The linear approximation of f of x2 is equal to f of x1 plus the derivative of x1 multiplied by the difference between x2 and x1. And again, this formula comes directly from the point-slope formula for the equation of a line, so if we can remember that formula, this one should be pretty easy to remember too.